Here we are going to cover only the oxidation reactions for alkenes, and oxidation reactions are specifically here the oxidative cleavage. Okay, so this is the smallest section of alkene reactions. So you remember all the reactions that we have done so far, or maybe you're still catching up, but we have done all of these reactions, and what I'm going to focus on now is this portion here, which is called the oxidative cleavage. So one of the last reactions to do now for alkenes is oxidation. And this oxidation is not just oxidation, but it is actually oxidative cleavage, which means that you're also doing oxidation and you're also cleaving the alkene. We'll be using two reagents over here. One is with ozone, and the other reagent we will talk about is going to be KMnO4, okay, which is potassium permanganate, but this is going to be hot potassium permanganate, okay, so we'll talk about that. So the first reaction that we will do is with ozone. Ozone is the reagent. The workup is going to be with zinc and acetic acid. Okay, so that's what you will see on the reaction arrow. On the top is ozone, and the second is zinc and acetic acid. In some cases, you might even see dimethyl sulfide. Depending on who is making the question and who's writing and who's using these reactions, you can use different kinds of workup reagents. But your main reagent is ozone, okay, over here. So here are two kinds of alkenes that we'll be working with, of course, the symmetric and the asymmetric, okay? So here, if you have this kind of a symmetric alkene, which is CH and then double bond CH2, then when you cleave that with ozone, you end up getting two aldehydes, okay? So what we're doing is just we are breaking this double bond, and in that double bond, you place oxygens, okay? So you end up getting two aldehydes in this case. When you have a carbon that is substituted, okay, on the double bond and another carbon that is not substituted, then when you cleave this one, there's no hydrogen on the left carbon, so which means that you will end up getting a ketone. Okay, if there was a hydrogen, then you would get an aldehyde, which is what you see here. So which means that if both of these were substituted with carbons completely, you will end up getting ketones. Okay, so you can get aldehydes and ketones, and also ketones. Okay, so depending on what kind of an alkene you have, not substituted, partly substituted to completely substituted, you can get different kinds of aldehydes and ketones. So make a note of that. All right, and so the mechanism here, which I don't need you to memorize the mechanism here, but just kind of see what's going on over here and how the double bond is breaking, is that here is the ozone, okay, and ozone will add on to the alkene, and this kind of a mechanism is like a concerted mechanism, okay, which means you don't know which arrow came first and which arrow came second. So in any case, this concerted mechanism will then cause the breakage of this bond, and then each carbon is going to get an oxygen. Okay, now if you look at the starting material here, the alkene, it's completely substituted, and because it's completely substituted, you're expecting ketones. Okay, so here is one of the ketones, and then the other ketone will come from here once this fragment is worked up. Okay, and it goes away with acetic acid, so you end up getting the other ketone. Okay, so don't worry about all of this, because this is something that goes on in the reaction, but then once you work up the reaction, all of these intermediates will be gone. Here is the oxidation of alkenes with KMnO4. Now remember, we've done this reaction before with potassium permanganate to form diols. When we did this reaction with diols, we were careful enough to use cold temperatures or room temperature. In this case, what we're going to do is we're going to heat it up, okay, a little bit. So you can look at our reaction conditions. And so here is potassium permanganate in presence of a base and water and heat also. Okay, and you have to be careful to watch the conditions, because if you have KMnO4 cold, then you will get a diol, but potassium permanganate with heat will give you cleavage, okay, or oxidation. So you have to kind of watch out for that. All right, since potassium permanganate is a very powerful oxidizing agent, much more than ozone, it will give you even more oxidized products, okay, which means that we were stopping with aldehydes and ketones with ozone, but now here we can go all the way to acids. All right, let's look at this one first. Okay, here is a symmetrical alkene here with the CH and CH, which is also not completely substituted. So if it's not completely substituted and you have the hydrogens, now with KMnO4 you end up getting two acids, okay, over here. So in the previous case with ozone, we ended up getting two aldehydes, all right, but now we're getting acids because KMnO4 is more oxidizing, more powerful oxidizing agent than ozone is, okay. However, if you get an alkene that is substituted completely, then you can't oxidize that more than a ketone, all right, so you have to stop at a ketone. This one cannot go on to an acid, all right. However, if you have a terminal alkene, which means you have a CH2 group, that CH2 groups will get oxidized all the way to carbon dioxide, okay. You will get the acid if you have another carbon, okay, attached to the double bond. But if you don't have that, if you have a terminal CH2, that will give you carbon dioxide. So everything about potassium permanganate is more oxidizing. This reaction is also a qualitative test, okay? But we're not isolating the products in qualitative tests. You could, okay? Because this is similar to what we did in diol, okay? Except that we're not heating it, okay? In diols here, you are heating it also. Here is an example of how we actually use the oxidative cleavage. Okay, it's a very good way of working through structures of compounds. Okay, so for example, if you have an unknown alkene with a molecular formula of C7H12 and then you treat it with KMnO4, then you end up getting this product. Okay, in this case, you have a ketone over here and then you have an acid. So you have C7H12. Okay, that's your starting material, your unknown alkene, okay, with this molecular formula, and with KMnO4 it is giving you this product. So what is the structure, okay, of this product? So what you do is count your carbons first of all, okay, make sure that you have 7 carbons, which is 1 2 3 4 5 6 7 carbons, okay. And the fact that you have a COOH, which means if you have an acid, it means you have to have a more oxidized carbon, okay, which means a less substituted carbon. So the ketone is coming from a more substituted carbon and an acid is coming from a less substituted carbon. And the other fact is that because you have only one fragment, it means that you're starting with a cyclic structure. If you had a straight chain alkene, you would have 2 fragments at the end, but because you're starting with one molecule, which is cyclic, you're getting only one molecule at the end with the 2 functional groups. So now all you have to do is attach these 2 carbons where you have the double bonded oxygens, okay, and that's where the double bond is going to be. And so this is your starting material, okay, for this. So here's the CH3, that is the CH3. So this is the one, this is the carbon that gave us the ketone, and this is the carbon that gave us the carboxylic acid, okay. So that's how you kind of work this through, okay, and I'll work some more problems with you in class. So let's look at a couple more worked examples. What is the alkene that gives the following 2 products on ozonolysis? So this is kind of like a retrosynthesis, and a retrosynthesis would be, when you're writing this kind of an arrow. And so here, if we look at these 2 alkenes, we've got 2 ketones for us. So this is fairly simple because all you need to do then is join the 2 ketones together. Okay, because then this is your fragmentation that's going on. Okay, so that's a simple one, but that's okay. This is kind of a normal kind of a problem you will get where you are given the fragments and you're supposed to figure out the starting material. The second problem I have here is a little bit different. So let's read the problem. An unknown alkene with the formula C9H12 reacts with 3 moles of hydrogen to give the 1-ethyl-3-methyl blah blah blah, and the products below on ozonolysis. What is the structure of the alkene? So in this case, here is our alkene that we are starting with, and the alkene on ozonolysis gives these products on the right hand side, and then on hydrogenation gives the products you have on the left side. So the hydrogenation tells you that you have 3 moles of hydrogen being absorbed, which means that you have 3 alkenes, okay, in there. So if you look at the products, in the products you have a whole bunch of double bonds though, okay, and that will happen because you're going to have a lot of alkenes. And if you have 3 alkenes, then you're going to have multiple fractures. So let's go ahead and write this one out, because this is HCHO, which means that this is an aldehyde that looks like this. So when I'm trying to think about how to put all these 3 fragments together, I'm thinking about the HCHO first, because that is a 1 carbon fragment. So somewhere I broke off 1 carbon. So that 1 carbon can come either from here or it can come from here. Okay, so if it comes from, let's see, if it comes from 1 or 2. So if it comes from 1, then I have a different set of products. If it comes from 2, then of course it's different. So I'm going to go ahead and place it at 1 first and see what happens. And if everything works, I don't have to do 2. So let's look at this and put that there, and then put the methyl group where it's supposed to be. So which means that now I have broken off this fragment. So now I'll go ahead and number my carbons, because I need to figure out how many carbons I have in my product and so on and so forth. So 1, 2, 3, 4, 5, 6, 7. So that's in my ring. So here, if I break off from here, this carbon is then number 1, or this carbon is number 1, okay, because that's an aldehyde. This is the aldehyde, right? So that's gone. So I have an aldehyde here. So I have an aldehyde here, here, and here. So I have 3 aldehydes. So I need to figure out how it's going to work out. So now let's go ahead and number these carbons, okay, over here. So this is 1, 2, 3, 4, 5, and then this one is 1, 2, 3. Okay, so I have 3 carbons here, 5 carbons here. So, and remember, I have a carbon here also. Okay, so that's my 8th carbon, because that's 5 plus 3. So I have to worry about 8 carbons. Okay, so now if I look at this structure, I have a couple ketones over here. Okay, and the ketones that I have are here and here. This ketone and then this ketone. Okay, so I have 2 ketones. What does the ketone tell me? It tells me that I have substituted alkenes. Okay, so which means that I'm looking for more substitution there. So the only carbons where I have more substitution is carbon number 2 and carbon number 6. Okay, so those are the only 2 carbons which can give me ketones, okay, because those are the highly substituted carbons. All right, so which means that I can have a double bond on 3 and 2 or 2 and 7. Okay, so those are the places. So I can say, okay, I have a 5 carbon fragment. So if I just keep working my way through 1, 2, 3, 4, 5, and if I have a 5 fragment, so on the second carbon, I have a double bond, and then on the 5th carbon, I have a double bond, right? So here I'm going to make an aldehyde, and on the second carbon, I'm going to have a ketone. So the second carbon here, number 2, that has a double bond right there. So if that is it, and then if I cleave it like this, that should give me a ketone. Okay, fine, that sounds good. So let me see if my products are all going to be fine now. So on 5, remember, I have an aldehyde. This 5 over here, this is an aldehyde. So if I fragment this here, then on carbon number 7, I'm going to have an aldehyde. So which is this carbon. So this carbon is carbon number 7. And then carbon number 6 is going to be a ketone, which is, this is carbon number 6 now. And then this one that I've circled here, that is carbon number 3 here. Okay, so now this is all working out. So which means I don't have to work out for if I were to fragment over here. Okay, so this just happened to work out like this, but sometimes it takes a little bit work. Usually in an exam or something like that setting, you will have a little bit not as involved, okay, of problems like this one, because this is a little bit more like for a homework kind of a problem where you have some time to put all the fragments together. Okay, so that's a nice example. Okay, so now that you know all about alkene reactions, let's just talk about a couple qual tests. And qual qualitative tests that are used to determine functional groups, and usually what happens with them is that they're visual, right? Visual means color change, precipitation, gas formation, anything like that is what gives you a qualitative test. So for an alkene, if you add bromine to the alkene, bromine is a dark colored liquid, dark red colored liquid. So if you add bromine to an alkene would add on the bromine. So if you're adding on the bromine is getting consumed, so the color is going to disappear. Okay, so that is a nice visual test that you have an alkene. Alkane is not going to give you a positive. Similarly, with the KMNO4, there are two tests possible with KMNO4. Both will give you the same results. So whether you take KMNO4 at room temperature or you take KMNO4 and heat it, it doesn't really matter because the products are going to be the same. How so? So KMNO4 in cold gives you a diol. KMNO4 in heat with heat will give you the fragmentation of double bonds. Okay, so KMNO4 is a nice purple colored solution, really deep purple colored solution. So once it reacts, KMNO4 is the oxidizing agent, so which means that it is giving oxygen, it is oxidizing something else, which means it itself is getting reduced. Once it gets reduced, it becomes MnO2. So remember, it's oxidizing, so which means it loses oxygen. The MnO2 manganese dioxide or manganese 4 oxide, this one here is kind of like a brown precipitate. Okay, and so there are two visual things that are happening here. The purple color is going to disappear because KMNO4 is no more, and then you will see the precipitate of the MnO2, which is a brown colored precipitate. So you see two things there. So what are the keywords and concepts to take away? Of course, you should know the oxidative cleavages. You should know the reagents that are responsible. So ozonolysis, KMNO4, those are the two common reagents you need. And then we talked about qual analysis just now. So those also you should understand, because qual analysis may not be given as by itself, but you use that in addition to some other information that's given to you.